Okay. First of all, thanks a lot for the invitation. It's great to be here, and I feel privileged to have the opportunity to tell you a little bit about my work. As Ivan said, we've had some great talks already. It's a tough act to follow. I'll do my best, but actually Ivan has given me a brilliant introduction, so maybe I'll make it through my talk in time, more or less. How does that work? Okay, here's a broad motivational slide. This shows the sort of performance efficiency records for different types of solar cells. And up here you get the really expensive multi-junction ones. They're great, they work great in space technology, but people don't have them on the roof. What we kind of see as practical devices of the conventional silicon basis, they're also great, but they're kind of expensive to manufacture. And they don't have the flexibility. So I think Ivan made a case for OPVs. They're down here. They've been around for about 30 years. And there's been exciting progress. And some have quite respectable efficiencies of up to 15%. But most of them are actually in the low single digits. And there's a reason we don't have them as devices. And unlike display technology, if I look at my mobile phone here, that's my iPhone that has an OLED display. When 6-7 years ago my phone didn't, and maybe your TV is OLED now, we've not sort of really seen that revolution in light harvesting of for solar cells. So why is that? Part of the reason is the efficiency is rather low. And can we do anything about it to make that a more viable technological prospect? So that's this is a practical motivation. Now I'm going to go very sort of blue skies and kind of move away from that, but that's a big motivational slide. So are organic materials good at light harvesting? And I think we know the answer is they can be in a certain way. So this is again the purple bacteria photosynthetic apparatus, and I'd like to point your attention to these ring-like antennae, which Ivan discussed. You see why I've got that up there. So in what way is nature perhaps doing better than we do with our light harvesting? And one of them is absorption cross-section. Nature actually has quite strongly absorbent materials, and once you've absorbed a photon, you create an exciton. You need to move it to an interface where charge separation happens in organic photovoltaics, and in our artificial technologies, a lot of the excitons get lost through non-radiative and radiative recombination. In photosynthetic organism, that doesn't really happen. Nature is better at channeling these excitations to where they need to be. And part of the reason might be the super transfer, but it's the kind of the arrangement. And finally, actually with organic materials, you can quite easily break the detailed balance. One limiting factor in the efficiency, this is for certainly silicon solar cells, is we've got the fact that a good absorbing material is a good emitter in semiconductors, and we lose some efficiency that way. That's the blue region here and the Shockley-Queisser limit. So this is a relatively easy win. So there's a lot of interesting stuff that could be said about all three of these topics. I don't have time for that. And I think what I'd like to do, I'm going to focus on the first one. I'm going to talk about absorption and some loose bio-inspiration. And I'm going to go quite far away from the biological systems in a minute. But I'd like to tell you a story that has its roots in Australia, because it started a little bit over 10 years ago, talking to Gerard Milburn and Tom Stace at UQ. And we were kind of looking, and that's before I knew Ivan, so this is why we kind of maybe got it a little bit wrong, but we were looking at these purple bacteria ring antennae and kind of asking ourselves the question, what are they good for? What can you do with them? So here's my simple schematic. I've got a ring of 6 absorbers/emitters. I'm going to model them as 2-level systems with a ground state and excited state of transition frequency. That's highly idealized, of course. And then if they're all the same, but they're sort of relatively far apart, and if you think about emission first, if you start them all excited, what you expect to happen is see an exponential decay in the intensity on the populations. Now things change when you put them very close together, and if they're completely indistinguishable, at this point you get, apologies, it's too far, you get a super radiant pulse, and you get the energy out a lot faster. So this is all well understood, by the way. There's a great review paper by Gross and Harosh from the 80s, which kind of discusses that. So what was our thinking on that? We said, if you have a really good emitter here, in these ring-like arrangements, maybe you can invert that and get a good absorber. So we kind of looked at a ring-like arrangement. Here's a schematic. We got it wrong by kind of thinking of, actually we didn't think about the direction of the dipoles at all, but if we'd thought about them, they'd be out of the plane, not tangential. And we kind of said, so where does the interesting stuff happen? When we think about the superradiance, we can look at this ladder of it's known as Dickey ladder states, where we just count the number of excitations we've got on the ring. So again, this is going away from nature. You don't have multiple excitations, but we've got no excitations on the ring, one, etc., until we're every two-level system's excited. And the quantum enhancement kind of really happens near the midpoint of this ladder. This is where we have optical rates which scale as n squared rather than n. And that's where the interesting stuff happens. For the superradiant case I showed you, we cascade down and we kind of go through that regions. For absorption, most of the time, we'd be sitting down here and it's hard to make use of that. So what was our idea? This is actually where the ring now matters. Everything I've told you didn't really need the ring. What happens in these rings, you have dipole-dipole couplings, and the molecules are quite close together. Normally, when you have interactions, superradiance kind of disappears. You get a sort of spectral fingerprint, right? The emitters are no longer completely indistinguishable. That's bad. In this case, however, you've got perfect symmetry, and each site has the same set of pairwise interactions with all the other sites as any other site. So they're all still equivalent. And what that means is this kind of Dickey ladder picture still holds, but what we now get, we get energy shifts, and the frequencies are all different and unique as you kind of move up or down the ladder. And what we thought in this paper, what that might enable us to do is target a transition near the middle of the ladder and kind of either enhance that or suppress the transitions adjacent below and do some kind of spectral engineering which might allow us to enjoy this super absorption effect, as we coined it. So that was an interesting idea. The problem is, when you kind of think about condensed matter structures, it doesn't work. And what we've treated our sites or our emitters, absorbers as two-level systems. We haven't thought about the vibrational environment or kind of anything reflecting the condensed matter nature. Once you do, you're no longer confined to this Dickey ladder of states. You will move away from it, and that destroys the effect, unless, and this is what we found, what we thought about a few years later with my former student Will Brown, you tilt the dipoles. So now we're thinking about the direction of the dipoles. They're no longer all out of the plane. We've got them tilted in such a way that the nearest neighbor dipole terms become negative. And in that case, we go from what chemists might call an H aggregate to a J aggregate. And in this case, actually, our sort of Dickey ladder states, or the states that have a lot of overlap with the ideal Dickey ladder states, they're now lowest in energy in each excitation manifold. So now I'm showing you the full state space of a ring of 4. And what the phonons now do, that's these sort of purple arrows here, right? They kind of, vibrational relaxation kind of pushes you onto these states. And then you might still actually get collectively enhanced optical transitions kind of near the middle of this ladder. So does this work? I'm not going to talk through the details too much, but we try to benchmark that. And kind of what we find is, basically in this paper, we do get a superlinear transition dipole strength, kind of near the middle of the Dickey ladder. It's no longer quadratic, and that's because we've tilted our dipoles. They're no longer all parallel. But it's better than linear. That's the orange line here. This is what I'm talking about for this tilted arrangement. It doesn't kind of get close to the Dickey ladder. And if I only look at this bar chart on the right here, this is showing you the net generated power per two-level system in the ring. And as we make our rings larger, we see we get more power per absorbing dipole. So we get more than the sum of the parts, and we have a kind of super extensive or super linear behavior. So we're pretty pleased with that. Well, maybe that's kind of might be the way to go. We actually now think, we've paid a price, we've gone down from kind of here to there. We now think you can actually maybe have your cake and eat it and get the same effect without sacrificing dipole strength, but that's a different story, not for today. No one's done this because it's kind of hard to do. You need to engineer the right kind of molecule maybe, or kind of nanostructure. I think it's doable, but hasn't been done. So I'm going to move to a different setup, which is a second connection to Australia, and that's work done in collaboration with our conference chair, James. with experimental colleagues in Milan, Sheffield, and the theory with colleagues from St. Andrews. And there we're trying to see the same kind of collective absorption enhancement, but in a different way. So here's the animation a former PhD student of mine produced. I found it on LinkedIn. She didn't tell me, but I thought I'd use it for you anyway. We imagine we've got an ensemble of organic dye molecules in a microcavity. It's Lumogen of orange and a commercial dye. We shine laser photons into the cavity, and the question is how quickly can we convert those laser photons into molecular excitation? Right, and I'm going to say, we called it towards quantum batteries, because the idea is we are converting light to an electronic excitation. The idea of the quantum battery, I think there's talks on this tomorrow, is if you make the battery twice as large, you make the capacity larger. Not only can you charge it maybe in the same amount of time, but you can change it faster, charge it faster. So that's what we'll be looking for. Anyway, this is the fancy sort of animation I stole off LinkedIn. Here's a proper theoretical model. We've got our molecules in a microcavity. We model them as two-level systems with decay, with pure dephasing. We shine in a short laser pulse to get photons into the cavity. And what we're interested in is, here's a laser pulse. How long does it take after the arrival of the pulse to achieve molecular excitation? We might measure the time till we're kind of half the way up or till we've reached the maximum. And we're going to call that the charging time. And I think that's going to be tau on a subsequent slide. Apologies for the inconsistency. We can write down a pretty idealized theoretical model, essentially based on a sort of Lindblad master equation. I'm not going to talk through the terms for it doesn't really matter for those of you that know Lindblad equations. You recognize it. There's two challenges with that. One is we're dealing with a large number of molecules here, and I don't mean 5 or 7. Right? We're going to be talking about 10 to the 10 to 10 to the 11. So that's one of the challenges for kind of solving this. The other challenge is there's a lot of unknown parameters, or there's a lot of parameters in the model. Some are known relatively well, and some are not really well known. But this is based on this. We developed a theoretical model based on a second-order cumulant expansion, which gives us an ability to kind of change that large number of molecules and see what happens. And this is the theoretical curve. We've got our charging time tau here, and maybe we're scanning the number of molecules through this. Oh, I can't see the line. There it is. We're changing the number of molecules in the cavity, and we kind of monitor what happens. And now we're in this green region where the charging time goes down. Initially it goes up, then it goes down, and then it kind of, in the red region, it levels off. And that's actually a region we don't want to be in for reasons we understand. But the point is we've got the right number of molecule, or the right kind of interval. We've got a charging time which goes down as we put more molecules in the cavity. That's your quantum battery. You increase the capacity, time to charge decreases. So this is the theory. What about the experiment that was done in Milan based on devices from Sheffield? And it's looking at kind of two classes of different kind of microcavities with different concentrations of molecules. So the experiment changed the number of molecules in the cavity, and then pump probe spectroscopy kind of tells you how many of the molecules are excited. And this is the recorded experimental data with a theoretical fit. And if we kind of try and relate it back to the animation I showed you on the previous slide, we don't have very many data points, but we do have a few. And those fall on our theoretical lines. And we can, in particular here between A2 and A1, we can see as we double the number of molecules, we see a decrease in the charging time. So arguably we've got the effect we were looking for. So that's the work done with James, and I think that's an experimental demonstration of superabsorption. And it maybe represents the charging stage of a quantum battery. Okay. Can we do more? Can we do different things? I'll tell you. Oh yes, and we do get our fitting parameters out. So, can we do different things? Yes, this is preliminary results with my postdoc Nick and my colleague Peter from Strathclyde in Glasgow. So what we're looking at here is we've got a number of two-level systems in a cavity, and instead of shining in a short intense laser pulse, we now apply a CW coherent drive on the cavity. And what we found is I'm not sure the colors come out nicely. What we found is that in the mean field limit, if we have an infinite number of molecules in the cavity, and we map out the excitation state of the or population of the two-level systems as a function of the drive strength on the cavity and the decay rate of these two-level systems, there's a region of bistability here. And that's a little bit hard to see, perhaps. But there is hysteresis, there's a region of bistability, and this kind of maps it out more clearly in a top-view way. So there seems to be a dissipative quantum phase transition. In this model, it's a coherently driven Tavis-Cummings model, basically. So that's in the mean field limit. What happens if we go to finite n? And then what we're looking at here is numerical simulations where we do increase the number of two-level systems in the cavity from about 2 to 20. And for fixed time, we see actually in this bistability region, as we increase the number of molecules, we get closer to these kind of two branches of the hysteresis curve in the mean field level. So we do have two branches with different behavior. If we keep the number of two-level systems fixed and we increase time, eventually we will converge onto a unique steady state for any finite size. So why is this interesting? We can now initialize our system in one of these two branches inspired by the mean field. This should be an n, not a beta, apologies. And then we see our branches decay onto the steady states, albeit at different rates. Depending on where we sit, if we tune beta, we decay fast, or we decay very slow onto the steady state. And the larger n, the more molecules we put in, the slower we converge on the steady state. So we kind of get closer to this mean field behavior. And so what we thought we might be able to do with it, if we initialize in a state with a large molecular excitation, but the molecules can decay, and then we watch the decay onto the steady state, how much kind of excitation can we extract before we've reached the steady state? And we take that as some measure of a transient superabsorption effect. So what we're integrating is getting rid of some short-term dynamics. We're integrating this kind of essentially exponential approach to the steady state. If we analyze that, what we find is an interesting scaling in terms of n. And what we see here is, so this is the kind of extracted molecular excitation until we get to the kind of, until we've reached the steady state. It's a transient effect, it only happens once. But as we increase the number of two-level systems in the cavity, this goes up, in this case, not quadratically, not polynomially, but actually exponentially. And that's, I think, to do with the first order phase transition, where we see a pretty drastic effect. So this is maybe a superabsorption effect under a different guise for a model which is actually quite similar to the quantum battery one, only now we're doing CW drive. I'm running short on time, so I should move on. This is preliminary results, but hopefully we'll post something soon. Is it useful? I don't know. I think it's interesting. Other things, I'll take 2 minutes to shamelessly plug work I didn't have time to talk about, which kind of maybe meets the other banners. So I haven't talked about dark state protection. I think that can work for long-range transport, and we've done some work where the interplay between a collective electromagnetic and sort of more localized vibrational environments leads to dissipative, coherent dissipative dynamics, the dissipation matters, where you can kind of very slowly essentially crawl through a number of dark states and you reduce loss, and you might be able to get your excitons further. So we've got some papers on that. And then here's sort of other bio-inspired quantum photocells we looked at, which again build on the dark state idea. These are proposals out there. They all work on the principle of breaking detailed balance. We can create materials which can absorb well, but they don't emit equally well. That's the sort of idea. And you might be able to kind of even daisy chain that and do it multiple times. On the right, we are sort of talking about ratcheting. So, final thing to say before I'm going to wrap up is, here's a very different study I contributed to a couple of years ago, and this is, once again, you see the ring-like antennae of the purple bacterium, and what we were thinking about here is that potentially useful for lasing. So for a long time, people have been interested in sunlight-pumped lasing. What if you don't need to create a pump? You can use ambient sunlight to drive your laser. That would be interesting for a number of things, for getting greener lasers in some sense, maybe communication, maybe energy harvesting, maybe driving chemical processes. So it can be done with big concentrating optics, and usually people use big mirrors, and there's kind of heat management problems, etc. So what these photosynthetic antennae are very good at, they're essentially sort of nanoscopic sunlight collectors. They're nanoscopic lenses, which can grab your solar photons, and they channel them to the reaction center. And really the core idea here is, if we take this system and we can passivate the reaction center, and chemists know how to do that, I don't, and then attach an organic lasing dye, then we might have a gain medium where each lasing molecule has its own kind of nanoscopic lens or nanoscopic sunlight collector. And this is based on theoretical calculations with the sort of right modified biostructure. It may be possible to achieve lasing with natural sunlight, ambient sunlight, without any concentrating optics. So we're currently trying to see if we can get funding to do this. So this is theoretical calculations, whether we can do this experimentally. I think I'm out of time, so I'd better wrap up. So I guess a broad summary here is my interest span towards loosely bio-inspired quantum energy tech, if that's a thing. And here's the examples I kind of talked about. I don't have a suitable picture of the people who did the work. I don't have them all on the same photo, but I should say, of course, it's a big thanks to Kieran Higgins, Will Brown, Dom Rouse, and Nick Warren, who were instrumental. This is an overview of the interest in my group, and I'm currently looking for a postdoc and for PhD positions. And with that, I'll finish my talk. Thanks very much for your attention.
We have time for a couple of questions. We've got one in the back over here, over there.
Thank you very much for the talk. It was very interesting, and I wish I could have heard more about the breaking of the detailed balance.
Yes.
Perhaps a naive question, but can you explain why for the superabsorption in the quantum batteries, why, as a function of n, the charging rate is not a monotonic decline, and what the initial rise, what is that?
Why do we get the little hump? I'm not entirely sure, to be honest. The model is sort of slightly more complicated. And actually, maybe something to stress is this is also, it relies on dissipation. So kind of linking to, if we had a perfectly clean system without any dissipation, we would kind of expect collectively enhanced Rabi oscillations. What we kind of get is sort of just this half oscillation. So the dephasing in the molecules and the loss rate kind of we kind of move up, and then the dynamic stops. Why we get this little hump, I'm not entirely sure, but that's what our sort of full theoretical model tells us. We do understand why things kind of slow down as you increase the number of molecules further. But yes, the curve is slightly more complicated, doesn't just show the increase. But if you're in the right region, where you want to be is sort of just on the boundary to strong coupling. So we don't want to be in the strong polaritonic regime where we can't really tell matter from light excitations apart anyway in a meaningful way. That's the red region. And then we'd need to, we got polariton shifts, we'd need to change the frequency of the laser sort of dynamically, so we need to chirp our pulse. That's the red region. We don't want to be in the weak coupling region where we don't have enough collective enhancement to really benefit. So there's a sort of Goldilocks green zone, that's where it goes down. The little hump, I'm not entirely sure.
Thank you.
Hi, thanks. Yeah, just a question on the superabsorption. If you have different orientations of the dipoles,
yes,
or local dephasing, that can take you outside the Dickey space.
Yes.
So I've wondered if you've thought about engineering sort of ways to suppress that, or to take advantage of the fact that maybe you could try to resymmetrize it in some way.
So absolutely. I mean, the dephasing, any dephasing takes you off the Dickey states, and that's maybe the the problem with the kind of, I guess, our original proposal for superabsorption is it's not robust to noise or any kind of imperfection. So I think where we kind of fixed that, in some sense, is by tilting the dipoles. We saw there's what we call the guide slide superabsorption, and then we went from H aggregate to J aggregate. And what you have there is the collectively enhanced states are lower in energy. The bright states are lower in energy than your sort of the darkish states. They're not completely dark. For that, I can't go back to my slide now, but I kind of had these little sort of violin blobs kind of on the transition dipole strength. What these represent is about 10% kind of relative disorder on pretty much all of our model parameters. So pretty much anything we do, once you're sort of in this J aggregate configuration, you're suddenly robust to noise, you're robust to dephasing, and the reason is vibrational relaxation can always pushes you back. So you slide downhill in energy. Of course, that's more effective at cold temperature, but it can be, it could in principle work at room temperature. So yes, any noise takes you, any disorder in your parameters takes you off the Dickey ladder. The easy way to fix that is to go from H to J aggregate, and that's where thermal relaxation will kind of stabilize the effect. So we do now think you might be able to achieve that by keeping the dipoles parallel and keeping the collective dipole large if you kind of put a little a metal sphere in the middle, and then you kind of work out, and you may be able to have a large collective dipole and sort of negative nearest neighbor couplings. But happy to talk about that more later. But yeah, it's a very good point.